Welcome to the Explainer. Have you ever stopped to actually think about the invisible magic surrounding us literally every single day? And no, I'm not talking about wizardry here. I mean the everyday magic of physics. Specifically, we're talking about those incredible invisible magnetic fields that we have somehow learned to manipulate and command completely at will. It's this awesome power that operates totally silently in the background of our modern lives. And today we are going to unlock exactly how it all works.
Let's kick things off with a bit of a mystery. Picture this everyday scenario. You're walking across a sprawling parking lot. You press a tiny plastic button on your key fob, and from 50 feet away, you hear that satisfying, heavy mechanical thunk as your car doors lock. Now, how exactly does a tiny, weak electrical signal traveling through the air suddenly translate into the brute physical force needed to move a heavy steel locking mechanism inside your car door? The answer, surprisingly, lies in an invisible force of physics that we can literally turn on and off.
All right, let's dive into this. The answer to our car door mystery actually lies in a remarkably simple device, the electromagnet. By definition, an electromagnet is just any device that produces a magnetic field as a result of an electric current. Its ultimate superpower is astonishingly simple. It's basically a magnet that we can turn on and, crucially, turn right back off again. It's entirely under our control.
So to really wrap our heads around how we harness this superpower, we've got to rewind to the 19th century. A scientist named André-Marie Ampère was super fascinated by early discoveries in electricity. He decided to investigate what would happen if he took two parallel wires and sent opposing electric currents through them. Would they just sit there? Would they attract each other? I mean, imagine his sheer excitement when he ran the experiment and actually saw the two wires physically push away from each other. They repelled. Electricity was literally creating a physical, moving force.
The underlying physics rule at play here all comes down to interacting magnetic fields. When two magnetic fields interact, they create a force. It's really that simple. If the invisible magnetic field lines are pointing in the exact same direction, they push against each other, creating a force of repulsion. But conversely, if the field lines point in opposite directions, they create an attractive force. So in Ampère's parallel wires, the magnetic field lines between the wires were pointing in the exact same direction, which physically forced the wires apart.
Okay, so if a straight wire creates a simple magnetic field, what happens if we take that same wire and bend it into a loop? Well, if you scatter iron filings around that loop, they perfectly reveal the invisible magnetic field, forming these really distinct circles around each side of the wire. But notice the center. Right in the middle of the loop, all that magnetic force concentrates and points straight through.
Which brings us to a really crucial question. What if we don't just stop at one loop? What if we literally stack them? Enter the solenoid. A solenoid is simply a coiled conductor, just a long wire wrapped into many, many loops. By stacking those loops, that straight-pointing magnetic field in the center of each individual loop compounds. It all adds together. And the result? You get a highly concentrated, directed magnetic field that operates exactly like a standard bar magnet, but, and this is the key, it's powered entirely by electricity.
This is honestly the real aha moment of the whole explainer. Think about a standard permanent bar magnet, like the one stuck to your refrigerator right now. It is always on. It's static. It's completely inflexible. It will constantly attract metal whether you want it to or not. But an electromagnet, created by our solenoid, is switchable. It's dynamic. It is entirely controllable. We've essentially created an electrically powered magnet that only acts like a magnet exactly when we tell it to. The sheer utility of this is just staggering.
All right, I want you to actually participate for a second. Seriously, hold up your right hand right now. We're going to do the right hand rule for a solenoid. It's incredibly simple. Step 1, hand up. Step 2, imagine grabbing a coiled wire and wrap your fingers in the direction that the conventional electric current is flowing. Step 3, look at your thumb. Whichever way your right thumb is pointing, that is the exact direction of the north magnetic pole of your newly created electromagnet. It's that easy. Fingers follow current, thumb points north.
So now we know how to direct this force, but how do we make it massive? How do we build a truly powerful electromagnet? Well, there are three absolutely crucial ingredients. First, increase the number of loops in the coil. Sometimes we're talking several thousand loops. Second, pump up the electric current. And third, and honestly most importantly, introduce a core made from a material like soft iron. Why soft iron? Because it concentrates the magnetic field. And amazingly, it magnetizes incredibly fast when the power is on, and demagnetizes just as quickly the second you flip that switch off.
Section title: Solenoids in the Real World, Pushing and Pulling. Okay, so we know we have a switchable magnet that can pull things toward it, or push things away. Now let's see how this invisible magic actually operates the devices we rely on every single day.
First up, audio. If you've got a surround sound system, you probably have a subwoofer. This is a speaker totally dedicated to producing only low-frequency, really deep bass sounds. Now, to produce deep sound, you have to physically move a ton of air. You have to create longitudinal vibrations, specifically compressions and rarefactions in the air. To do this rapidly and with enough brute force to rattle your living room windows, the subwoofer relies on a highly specialized solenoid known as a voice coil.
Inside that subwoofer, there's actually this fascinating little mini-action story playing out. At its core is a permanent circular magnet surrounding our solenoid, the voice coil, which is physically attached to the speaker cone itself. An amplifier sends current into the voice coil, creating a magnetic field that repels against the permanent magnet, violently pushing the cone outward to compress the air. Then, literal milliseconds later, the amplifier reverses the current. That reverses the magnetic field, pulling the cone rapidly back in. This cycle repeats continuously, converting those electrical signals right into the physical compressions and rarefactions that create the deep bass you can actually feel in your chest.
Let's shift gears to another classic application, the old-school electric bell. The design of the electric bell is absolutely brilliant because it solves a very unique problem. It doesn't just need to strike once, it needs to ring continuously for as long as the button in, say, the principal's office is held down. It achieves this by using a solenoid to rapidly and mechanically turn itself on and off.
Let's walk through this rapid-fire mechanical flip book, right? Step 1, the switch closes, current flows, and the solenoids, which are amplified by their soft iron cores, instantly magnetize. Step 2, this sudden magnetic force attracts a soft iron armature, pulling it forward so the attached hammer actually strikes the bell. Ding! But here's the absolute genius part. Step 3, as the armature pulls forward, it physically pulls away from its electrical contact point. The circuit is broken. The electromagnet instantly turns off. A spring then snaps the armature right back into its original position, which completes the circuit all over again. The magnets turn back on, and the entire cycle repeats, over and over, delivering that continuous ringing sound. And you know, this brings us full circle, right back to our opening mystery. Your car. Solenoids are literally everywhere inside your vehicle, acting as switches and actuators, which are just devices that exert a physical force. When you turn your key, a solenoid acts as a switch to initiate the massive starter motor, and then switches it off once the engine is actually running. Solenoids initiate the gear shifts in your automatic transmission. And yes, when you press that button on your key fob, a tiny electrical current briefly energizes a solenoid inside your car door. It creates a sudden, powerful magnetic field that physically pulls an actuator, unlocking your heavy metal door from 50 feet away. Mystery? Completely solved.
So the absolutely crucial takeaway here is that we have taken the invisible forces of nature, harnessed them into little loops of wire, and created dynamic tools that push, pull, switch, and power our modern lives. From the bass dropping in your favorite song, to the bell ringing at the end of the school day, to the secure click of your car door. I really want to leave you with this provocative thought. Look around the room you are in right now. Look at your appliances, your electronics, your tools. What other invisible magnetic forces do you think are quietly powering your world today? Keep exploring, keep questioning, and I'll catch you on the next explainer.